Hello, my name is Eleftherios Aggelopoulos and I'm a principal engineer at the Steel Construction Institute in the UK. Today I will be presenting this paper on the shear resistance of concrete dowels in composite slim floor beams, which was written together with Johannes Schorr and Professor Ulrike Kuhlmann from the Institute of Structural Design at the University of Stuttgart in Germany. Slim floor beams, or shallow floor beams as they are often called, are essentially formed through the use of a relatively shallow asymmetric steel section. A wide steel plate is often welded to the bottom flange of the steel section, and so the slab can sit on the bottom flange or on this plate. The slab can be either composite with the use of metal decking or from precast concrete elements. When deep decking is used in particular, surfaces may be routed between the troughs of the decking, and this is particularly beneficial in terms of reducing the floor construction depth. However, slim floor beams are rarely used in buildings currently, and this is mainly due to the lack of experience and the lack of specific codified design rules. However, in the new revision to Eurocode 4 Part 1.1, which is currently underway, new rules will be included dedicated for the design of slim floors. I would also like to mention a large European research project called SlimAPP, which was completed in 2019. The work presented today is essentially part of that project. The objective of that project of SlimAPP was to develop rules for the design of slim floor beams. And as I said, this project was funded by the European Commission and the Research Fund for Coal and Steel, and the project partners, other than the University of Stuttgart and the Steel Construction Institute, were the University of Trento in Italy, the University of Bradford in the UK, ArcelorMittal and Astron Buildings. There are mainly two types of shear connection systems that may be found or used in slim floor beams. One is, of course, the use of conventional headed studs welded to either to the top of the steel section or to the sides of the web, as shown here. And the other type of system, which is shown here on the left, is by passing reinforcing bars through small circular openings in the web of the steel section, which are then filled with concrete. And this type of system is typically called concrete or composite dowel. So this type of connector is the focus of this work, and this is just a brief description of some of the push-out tests that were carried out in SlimAPP project. On the left-hand side, we can see a typical configuration used in those tests. There were already some tests carried out at the University of Stuttgart, but in SlimAPP we managed to investigate the role of more parameters. Some of these parameters can be seen on this table here. So the diameter of the web openings was varied between 40 and 80 millimeters. Different concrete strengths were used in the tests, and also the bar diameter was varied between 12 and 20 millimeters to investigate its effect. And you can see here some typical results in terms of the shear resistance and the slip capacity of the concrete dowels. And as you can see in this load slip plot, shown here, and also the from the slip capacity results shown in the table, presented in the table. You can see that this type of connector is really ductile, exhibited really good ductility in the tests. Also, some finite element analyses were carried out, again in SlimAPP, and the objective was to investigate the effect of certain parameters. Some of them I already mentioned, such as the bar diameter and the concrete strength. Also the spacing of the connectors and the geometry of the steel section. For example, it was found that the web thickness had a small effect, and also the flange width, the top flange width, had some effect in the resistance. There is more detail in the paper. Unfortunately, there is not enough time to present more detailed results here. The main objective was to develop a design model or a design expression for predicting the shear resistance of the concrete dowels, and there were a number of existing models available for similar systems, and these were obviously considered. However, it was found that there was quite a large scatter, so some models were able to predict the shear resistance of concrete dowels with greater accuracy than others. And this is demonstrated here, where on the vertical axis we have the shear resistance predicted by each of the models that are referenced, and on the horizontal axis it's the resistance obtained from the push-out tests. We considered a component-based resistance model. So we had contributions from the concrete and also from the rebar dowel action. And what we also found was that there are some additional effects contributing to the shear resistance, such as friction, although these it was not always possible to quantify them, to quantify exactly how much this contribution is. So two different models are presented in the paper. So this is the first one, and actually it is the model that we spend more time calibrating and validating. So it has there are two components. One is the rebar dowel action, so it's essentially the shear resistance of the bar, and we have it is multiplied by 2 because we have two shear planes essentially, and this is PR, and PC is the concrete contribution, which was calibrated against the test results essentially. So it was more or less fitted to the test results in this case, and this was calibrated or validated for a specific range of parameters, which are shown at the bottom of this slide. The other analytical model was more theoretical, but similar in principle. Again, we have PR, which is the dowel action of the bar, and we have again a parameter, a concrete parameter, which is essentially bearing of concrete against the web of the steel section. This alpha C factor is a concrete enhancement due to confinement, due to the concrete confinement, and the difficulty with this model is being able to predict a suitable friction coefficient, because as you can see, there is a multiplier which depends on the friction. So these two models are compared in these plots against the push-out test results. So we have the prediction on the vertical axis and the push-out test result on the horizontal axis. And as you can see in both cases, analytical model 1 is perhaps more accurate, but also analytical model 2, which is essentially equation 10 in the paper, is also conservative almost always. Also, some beam tests, some flexural beam tests and some shear tests were carried out in SlimAPP, and some of the details are presented on this slide. Again, there is more detail in the actual paper, but anyway, what was done, we carried out a back analysis of the beam test results to be able to predict the longitudinal shear force, the longitudinal force in the concrete, and we tried to compare it against that predicted using the analytical models presented earlier. And again, the findings are shown here. You can see that the predictions are quite conservative, almost always, and this suggests that there is also some additional contribution, for example, due to friction. However, when we tried, for example, to include that in a way, we found that in some cases the results become unconservative. So this is an area that requires more research in terms of quantifying the contribution due to friction and whether this can be used, or some of it can be used for the design purposes. So to conclude, the concrete dowel type of connectors exhibited high resistance and excellent ductility, as demonstrated in the push-out tests and the beam tests in the SlimAPP project, and the design models presented for the resistance of the concrete dowels were conservative, give conservative results when compared against the test results, and in some cases, such as in the case of analytical model 1, which is the equation 11 in the paper, the accuracy is relatively good when compared against the push-out test results. However, back analysis of the beam tests also demonstrated that there are other effects contributing, such as friction, which contribute to composite action. But as I said, more work is required in order to be able to quantify this. Okay, thank you for your attention.